so we're going to go ahead and start with chapter 1. Chapter 1 is going to be over matter, measurement, and problem solving. So the first part is we want to go over what atoms and molecules. So I'm sure everyone's heard of this before. Atoms are submicroscopic particles, and it is the building block of all matter. When you have one or more atoms joined together, you will make a molecule. So some cool molecules that we know of. All right, so with this here, you can see this is carbon monoxide, and that's carbon dioxide. So that's the carbon, that's oxygen, that's carbon and 2 oxygens. So one is poisonous, and one is something we breathe out, and plants use this. And for water molecule over here, we have H, 2 hydrogens, and 1 oxygen. And then you have an extra oxygen atom here, it becomes hydrogen peroxide. So basically, different arrangements of atoms can give you different kinds of molecules. Now, why is this important? So, carbon monoxide is toxic because of the shape it takes, and it can actually bind to the site where hemoglobin is, and that can give us problems, basically. So another example of cool molecule is basically our DNA. DNA is made out of all these little atoms here, and then we're connected in a double helix with different interactions between these atoms and molecules. And that makes us who we are. So let's talk a little bit more about chemistry. So chemistry is basically the study of atoms and molecules. Whenever you arrange the atoms differently, you will have different properties, and that can really change the functions or maybe toxicity of any molecules or atoms that we're considering. So another thing we want to consider is the scientific approach to knowledge. So I'm sure everyone's heard of this before, but let's go over the basic definition. So the first step is we want to have a hypothesis, which is a proposed explanation of what our observations are. To test the hypothesis, we'll have to do experiments. And then you confirm if your hypothesis is correct or not. Now, a scientific law or principle is basically something that we can use to summarize what we've seen in the past and predict what will happen in the future based on what we've observed before. Scientific theory, on the other hand, is basically trying to explain why certain things happen. Okay? Now we want to keep going. For chapter 1, we want to talk about matter. So we have basically matter is anything that occupies space and mass. We have 3 states of matter that we know of right now that we're going to consider in this chapter. We have solid, liquid, and gas. Basically, solid is close together. When atoms or molecules are joined really closely together, they don't have much freedom. Liquid is a little bit further apart. They have a little bit more freedom, and gas is really far apart, and they are able to move freely. So the next slide we have here is going to be talking a little bit detail about how the molecular picture is for solid, liquid, and gas, and basically what a physical observation we have. So feel free to go over this. This is something that we all have seen many, many times before. And under solid, we want to consider something over here. For solid, I want everyone to understand that we have 2 kinds of solids, okay? One is crystalline solid, and one is amorphous solid, okay? Amorphous solid has no pattern. It's just basically if charcoal is here, this is charcoal which is made from carbon, it's amorphous. It's just carbon atoms all over. There's really no regular pattern. Now, on the other hand, if you took carbon and you bonded it in a certain direction with a 3D pattern like this here, you can actually make diamond, okay? So carbon can make 2 different kinds of solids. In this case here, one with no pattern and one with pattern, or the one with pattern makes diamond. So under matter, we want to talk about pure substances versus mixtures. So over here, let's talk about pure stuff. So under matter, we have pure and we have mixture. So if it's not pure, it's a mix of two things, so that will be called a mixture. All right, let's go under pure substance here. Under pure substance, you have element and you have compound. So element basically is just one type of atom, okay? And then compound here is going to be comprising of molecules. So basically it will be like multiple atoms with different kinds, like in this case, water. Now mixture, on the other hand, we have two different kinds. One is heterogeneous and one is homogeneous. The heterogeneous is not evenly mixed, okay? And this one, homogeneous, is evenly mixed throughout the sample. So for example, a good example for these two here is when you think about sweet tea versus unsweet tea. Okay, so sweet tea is sweet throughout the whole sample here. So we call it homogeneous. Now, if you went to a restaurant and you asked for sweet tea and they say, sorry, we don't have sweet tea here. We have iced tea though, and we can give you a pack of sugar. So if you did that, you know when you try to pour the sugar into the cold tea, it doesn't really mix that well. So that makes for a heterogeneous mixture because the sugar is all on the bottom, not dissolved. And then on the top, it's just mostly just iced tea. Okay, so that's a not evenly mixed solution. So that's heterogeneous solution. And if it's, mixture. And homogeneous mixture is when you have an evenly mixed sweet tea all throughout the entire solution. It's homogeneous. Okay? Now, when we talk about mixtures, we have to have ways to try to separate them. So one common way to separate mixture is by using distillation. This is something we can actually do in lab, where if you have different kinds of liquids mixed together, but each liquid has a different boiling point. So what you do is you heat up the liquid here, and then as it reaches the lowest boiling point, the liquid with the lowest boiling point, that liquid will start to turn to gas. And if the gas hits a cold part of the tube here, how do you make it cold? By using a condenser here, where you put cold water circulating the outside of this tube here. Okay, so when the gas hits this cold tube, it turns itself back into liquid. And what is condensed over here is the pure liquid at that first boiling point. And then you can always separate this one out and then switch it with another container here, and you can actually boil up, increase the temperature, and you go to the next liquid, and then you can do the stepwise here by collecting different liquids of different boiling points. Okay? Now, another way to filter stuff, to separate mixture is by using filtration. One common way of using filtration is where we just use a funnel, and then we typically, if you use just, in this case, this is just a regular filtration, you'll want to go ahead and put a filter paper in this funnel here, and then you pour your mixture of liquid and solid. The solid will be stuck on the top, and then the liquid will go through on the bottom, and that's how you're going to separate the solid from the liquid mixture. In this case here, this is what we do in lab. But you know, when you're in the kitchen and you boil your pasta, if you want to separate the pasta from the water, you use a colander. So effectively, you are doing filtration in the kitchen as well. There's another term they call decanting. Decanting is separating the water, basically pouring it out, water, and separating it out, your mixture. When you pour, we call it decanting, okay? All right, so let's talk a little bit more about physical and chemical changes. Now, physical and chemical changes, we need to be able to tell the difference, which one's a physical change and which one's a chemical change. Make sure you try these questions out when you're doing your homework and your dynamic study modules, and of course, other questions that you'll see in the course. So physical change is when you change the states from solid, liquid to gas, okay? So the way it looks, it will change, but not the chemical composition, Okay, so if you boil water to turn it to steam, you're turning it from liquid to gas phase. That's a physical change. Dry ice subliming is turning from dry carbon dioxide, dry CO2, which is a solid, and then it will sublime into gas, which is just carbon dioxide gas. Sugar dissolving, so it's one piece of sugar cube, okay? And it's going to break down into multiple little pieces of tiny, tiny molecules of sugar mixed in with water. So we call it solid to aqueous. Now, aqueous is basically a phase where you have solid dissolved in water. Anything that dissolves in water is called aqueous, okay? So sugar dissolving will be considered just a physical change. So chemical change here, you have to change the chemical composition, okay? So for example, if iron is rusting, it's basically taking iron and then adding oxygen to it and you turn it into iron oxide, which is rust. And then if you have propane tank burn, the gas burning, you take propane, you have oxygen, you heat it up, and you get carbon dioxide and water as a result, okay? So here's some pictures showing you basically the physical change here from liquid state to gas state. Again, the chemical composition stayed the same as H2O, and that's H2O. The only difference is the spacing is a little further out now. All right, let's take a look at some more examples. So in this case here, they're a little smaller. Let me go ahead and try and zoom in for you. All right, so in this case here, that's dry ice subliming. It's a piece of dry ice, and it'll just, you see it start turning to gas, and that's from solid carbon dioxide to gas carbon dioxide, okay? And then when you take sugar and you dissolve it, it's a lot of pieces of sugar molecules all stuck together because it's in solid phase. And then when you put it in water, it dissolves. There's sugar and water molecules all around each sugar molecule, okay? And then this is propane burning. So the composition actually changes. You have propane, and then you end up with carbon dioxide and water in the end. Now here's a picture of iron, and then it rusts, turns into iron oxide. The chemical composition itself actually changes. So when it changes like that, the chemical composition, those are called chemical changes, okay? When the molecule doesn't change, like in this case, see how sugar stay as sugar? That's sugar still, so that's a physical change. And over here, that's carbon dioxide, that's still carbon dioxide. Those are physical changes. All right, so let's try and go over a few examples here. Let me go ahead and cover up the answers. All right, so the first question says, evaporation of rubbing alcohol, okay? Evaporation of rubbing alcohol, is this a physical or chemical change? I want you guys to try to figure this out. So take a moment, pause, and decide if it's physical or chemical. All right, so basically evaporating, rubbing alcohol is going from liquid to gas. So this would be a physical change, okay? Now, the burning of lamp oil, the fact that it says burning, what does it mean? Is it physical or chemical? In this case, when you are burning something, you will be changing its chemical formula. It's some sort of combustion. So in this case, this will be a chemical change. The bleaching of hair with hydrogen peroxide. Because your hair is changing color, right? And we're using hydrogen peroxide, your hair molecule is going to be changed by it. That's how it changes color. This is going to be a chemical change. Now, the forming of frost on a cold night. That's when it's cold, you have the air, the vapor in the air. It gets turned into liquid. And then and if it's cold enough, it turns to solid. So these are all basically physical changes. Okay, so frost forming on a cold night, when you see it on your car, that's all changing to solid phase here. This is going to be a physical change. Now, when you have another example is a dew formation. So dew is D-E-W, is basically in the morning when you wake up, you see like drops of water on the grass blades. Those are also physical change because it's basically overnight. Instead of turning to frost like cold, you're going to have just droplets of water, and that's a physical change as well, from no vapor turning to water. Okay? All right, so let's keep going here. We want to talk about measurements. So we have different units here for measurements, different quantity that we want to measure. So we do focus a lot on length, mass, time too, and temperature. Amount of substance, we will be focusing on electric current and luminous intensity, not so much, okay? So the SI unit is basically the international standard unit. Length, we use meter, mass, we use kilogram, and you wanna know the symbols as well, okay? So meter is M, kilograms is kg, seconds is S, Kelvin is capital K, mole here is the amount of substance, the symbol is MOL. Okay, a lot of students confuse this, so you have to remember amount of substance when you talk about moles, the symbol, the abbreviation for mole is actually MOL. You can't say M because M means meter. Okay, so it's MOL for mole. All right, let's go on and take a look at some more other units. So these are slides you can definitely want to just take a look over. These are just review material, just talking about all the different units of measurements and quantities that we try to measure. Just interesting facts here. We don't really need to really worry too much about it. So here's length. Let me show you a yard and a meter. And then we have mass, okay? Mass, we typically in our lab, we use units of grams, but the SI unit is gonna be kilograms. So I guess we wanna make sure we remember 1,000 gram is 1 kilogram. Okay, we'll be talking about prefix multipliers in the next few slides here, and I do want you guys to memorize the prefixes. Let's take a look at the next one, time. We use seconds to measure time. Kelvin to measure temperature, that's the SI unit, but we also, in our case, we use Celsius quite a lot. Okay, so I do want you guys to memorize the conversion between these units here, particularly between Kelvin and Celsius. Okay? So if you wanted to do, you want to change it to Kelvin, you take the Celsius and you add 273.15. Now if you want to do the opposite, you basically take the Kelvin number, subtract 273.15, and you get the Celsius value. All right, let's take a look at the scales of these guys together. Here we have the Fahrenheit scale, Celsius scale, and Kelvin scale. So what's cool here between Kelvin and Celsius is it goes up once, like if this one goes +1, that one goes +1. You see how 100 degrees Celsius from 0 to 100 is also 100 degrees Kelvin. The only thing different is always off by 273. Like if this is 0, that's 273. If this is 1, that's 274. If this is 100, that's 373. Okay, so when you go all the way down to -273 or 0 Kelvin here, 0 Kelvin is called the absolute zero temperature. Okay, on Kelvin, there's no negative scale. We go up to 0 and that's it. So the coldest you want to get here is -273 Celsius. And then Fahrenheit, you can see it's not the same. It's different amounts of degrees. So you would have to use the formula if you wanted to convert between Fahrenheit and Celsius. So an example here, it says we have 40 degrees Celsius, and we want to convert it to Kelvin and Fahrenheit, okay? So For Kelvin and Fahrenheit, I expect you guys to memorize the formula. If you needed to do the Celsius and Fahrenheit conversion here, I'll try to give you guys the formula if you can't remember that. Usually this will be available in the question itself, or you can pull up charts to look at it during homework time. When you have homework, you can take your book, it's open book, make sure you have your formulas, and you can use this formula to calculate it. Okay? So in this case here, to convert 40 degrees Celsius to Kelvin is you add 273, so you get this answer here, 313.15. And then we want to convert 40 degrees Celsius to Fahrenheit. So Fahrenheit is 1.8, whatever the Celsius, which is 40 degrees Celsius, and then plus 32. So these are our formulas here. You can get 104 right there. Now, this next slide here, I want everyone to memorize this, okay? You need to know some common ones, and then the rest of it will not be as common, but definitely try to memorize this. Try to start making flashcards and memorizing these prefixes and what they stand for, okay? So I'm gonna go ahead and show you guys what it looks like. Basically, if you put a unit of like grams or meters in it, okay? If you start at a base level here, so let me see. We have this note here. So if I had grams, okay? Oh, okay, I can fit everything. Let me zoom in a little bit. All right, so if I have grams here, that's my main unit right here. And then I wanted to write bigger units. The bigger units are all on top of that chart. So we start with kilo. What does kilo mean? So if you stick a kilo next to the gram, it becomes kilogram. For example, so that's kind of the way we're going to use our units. Now you can easily change it to another measurement. You can change it to meter. Now if you had meter, what would it look like? Well, it would be meter, and then you stick a kilo, it will be kilometer. Okay, so it's basically just you change this middle unit here, and you can apply your prefixes to different kinds of measurements. But we'll go with grams here, for example. Now, kilo means 1,000. So 1 kilogram is 1,000 grams, okay? And then instead of writing a bunch of zeros, you can just say this is 10 to the power 3, which is 3 zeros, 10 to the power 6, 6 zeros, and it goes up this way. So kilo is 1,000, 10 to the power 3. Mega is capital M, is 10 to the power 6. Giga, 10 to the power 9. Tera, 10 to the power 12. Peta, 10 to the power 15. Exa, 10 to the power 18. These are all bigger units. The more common ones that we will see, probably kilo, mega. Those are probably, the ones that are really, really common. But you definitely still want to memorize these bigger ones, okay? It's pretty easy to memorize because it's 3, 6, 9, 12, 15, 18. It goes up 3 each time, okay? So then you just go memorize this up here. So those are the ones that are getting bigger. Now, what if we want to symbolize it with a smaller unit? Instead of just plain grams, we want to talk about smaller units now, okay? So smaller units, we have deci, means 0.1 grams. So decigram means 0.1 grams, okay? So instead of writing decimal places, you can also write 10 to the power -1. And then you have centi is 10 to the -2, milli 10 to the -3. So milli is really, really common, right? Now centimeter is actually on your ruler. So I wanted to show you guys this. So we were talking about grams here. So let me take show you the meter right here. So centimeter, if you look on this rule here, it's kind of blurry. Can you see? It says cm, okay? That's centimeter. Now centimeter is 0.01 of a meter, okay? And then it says the next one is millimeter, 0.001, okay? So on your ruler, if you see a centimeter here, right here, this is 1 centimeter. That's 2 centimeter. that's 3 centimeters. So from here to here, that's 3 centimeters. Now these small little lines here are 1/10 of a centimeter. So those little markings are millimeters. Okay, so just want to keep in mind that you actually can see this on your ruler itself. So the small lines are millimeters. The bigger lines here are centimeters. So centi and milli is 10 off difference. That's why it's 0.01 and 0.001 right there. Okay, so those two are common. And then we also have micro. Micro is pretty common. We usually have micro in form liter, and you use micro pipettes. Okay, you have microliters, that's common. Nanometers are common too because it's nanotechnology. And then we have pico and femto. So femto is really common when you use femtoseconds for laser pulsars. Okay, so those are some common units that we'll have. Let's go back to the gram one and let's talk about the sizes for each one. So you have deci is 0.01, centi is 0.01, and then you have milli 0.001, so 10 to the minus 3. Let's just start saying this instead of all the decimals. So micro is 10 to the minus 6. Nano is 10 to the minus 9. So I want you guys to memorize what the prefix symbols are and what the prefix name is, and then also how much it means, okay? Like what the value is to it. Nano is 10 to the minus 9. Pico is 10 to the minus 12, femto is 10 to the minus 15, and atto is 10 to the minus 18. Again, the common ones are femto here, nano, micro, milli, centi. Those are pretty common. All right, so why do we need to know all these prefixes? Because we will be using them to do conversions. Okay, so I want to go ahead and give you guys a question that you might see basically maybe on a test or a quiz, something like that. So let's go ahead and write it out together. It's just a short one here, but I like to write out so you can take your time to write. If you're watching this video, you don't have much time, you can always fast forward. Okay, here's the question. It says, which of the following is shortest? Okay, and you have a few different options here. I have A, 3.0 nanometer, B, 300 picometer, C, 3.0 times 10 to the minus 10 centimeter, and then D, 3.0 times 10 to the negative 4 meter. So these are all in meters, right? And I showed you the list of the multipliers up here. Okay, so we want to go ahead and decide which one is shortest. So based on this list here that we just had, okay, nano meant 10 to the minus 9. So what my best strategy should be is to convert everybody to meters, and then I can compare apples and apples. Okay, so I'm going to go ahead and change all these guys out to just meters. So I have to find out what nano is, which nano, if you looked earlier, since we were doing meter, let's pull up the meter one. Nano means 10 to the minus 9. Okay, so I'm going to go ahead and just write 3.0 times 10 to the minus 9 meter. So that was a nano term right there. Okay, and then I want to go to convert pico, and I want to go ahead and use basically centimeter notation here. So I'm going to go ahead and do 300 is 3.00 times 10 to the 2. Agree? That's how you get 300. Okay, so that's 300. And then I want to times what pico means. And you look, and pico means 10 to the minus 12 right there. So I'm going to go ahead and say 10 to the minus 12 meter. Now when you have 10 to the minus 12 times 10 to the power 2, that equals to 3.0 times 10 to the minus 10 meter. Okay, so if here's 10 to the minus 9, here's 10 to the minus 10. Let's go ahead and convert this guy down here. Centimeter, but it's 3.0 times 10 to the minus 10, and then times the centimeter, which is centi stands for 10 to the minus 2. So this will be 3.0 times 10 to the minus 12 meter. And then you got 3.0 times 10 to the minus 4 meter. So based on this, if you want the shortest one, basically you will pick the smallest number. And which one is the smallest? 10 to the minus 12. 3.0 10 to the minus 12 is the smallest. So C here will be the shortest distance. Now, what if I asked you the question, which of the following is the longest? Which one will be the longest? Then you would pick the biggest number. Which one's the biggest? 10 to the minus 9, 3 10 to the minus 10, 3 times 10 to the minus 12, or 3 times 10 to the minus 4. In this case here, 3 times 10 to the minus 4 is the longest. So it says, which of the following is the longest? Our answer would be D. Okay? So that's why you need to make sure you memorize your prefixes right there. Okay, let's keep going. Now, the next thing we want to do is talk about some other units that we have. So we were just talking about the standard, like length, but we want to start combining units to make new units. So like volume is basically a combination of different lengths, okay? So if you had a cube here, the length times length times length, well, we call it width and height too, but you know, the measurements of the length each time, in 3D gives you volume, okay? So when it's 10 to the power 3, you get 1,000. So one thing I want everyone to go ahead and memorize here is that 1 liter is 1,000 milliliter, okay? And then 1 milliliter is 1 centimeter cube. So if 1 liter is 1,000 milliliter, that's 1,000 centimeters cube. It will save you a lot of time when you have to convert stuff. Okay, so that's right there. This one I want you to memorize. 1 liter, 1,000 milliliters is 1,000 centimeters cube. All the other conversions here, I wouldn't worry too much. If you needed them, we will give you conversions for that. But I do want you to memorize the metric ones, especially the prefixes. Okay? All right, so let's keep going. On top of this volume, we want to talk about density right here. So density is basically a ratio of mass to volume. Mass divided by volume gives you density. Density is an intensive property. So what in the world is an intensive property? Intensive property is where, like, no matter if you have a lot of a little bit of the stuff, that unit doesn't change. Like if you have a small rock or a big rock, the density of the rock stays the same. If you have a little bit of water versus a lot of water, the density of water stays the same. Okay, so that's the idea of intensive property. No matter how much the amount you have, the measurement independent, the value stays the same. Now, extensive property, on the other hand, on the opposite. If you have a little bit of it, it will be a small value. If you have a lot of it, it will be a big value. So like mass, if you have a small amount of water versus a big amount of water, the mass will be small for the small amount of water, and the mass will be big for the big amount of water. So not just mass, we can say volume, a lot of water, big volume, little water, small volume. Okay, so those are just extensive properties right there. So extensive properties, they change, depend on the quantity. Intensive property does not depend on the quantity of the matter, okay? So cool thing is density is going to be intensive. Other examples, maybe like boiling point, temperature, those are intensive properties as well. Now, over here, when we want to use units for measurements here for density, in lab, we will be measuring solid density If the solids are measured like with a ruler, you will use centimeter on your ruler. So we'll have centimeters cubed for our volume. So our units of density will be grams per centimeters cubed. And remember, 1 centimeter cube is 1 milliliter. So, and then on the other hand, if we use liquid to, we want to measure density of liquid, the volume of liquid will be in milliliter according to our graduated cylinder or burette, and we'll take grams divided by milliliters for the units of density for liquid. For gases, we tend to use grams per liter because the volume for gases is going to be bigger. Okay, now let's try a problem here. Oh, a couple problems on density while we're at it. So here's a question. Let's write it out together. A man receives a platinum ring from his fiancée before the wedding. He notices the ring feels a little light for its size. Personally, I just think that's strange. Most people are just excited about having a ring, but he noticed that his ring feels a little light for its size. Maybe like it felt like plastic or something. And then it said he decides to measure its density. Okay, he found out the mass. He just used a balance. You can take a kitchen scale and put your ring on it. It'll tell you the mass. In this case, he got it as 3.15 grams. Okay, and then he used a volume. He tried to get the volume. So in this case, you can use displacement because it's a weird shaped object. You can't really take a ruler and measure it. So you want to go ahead and fill your graduated cylinder with some water, and then read that number first, and then you drop your ring in there and you read the number again. The difference of that will give you the volume. Okay, so his volume here is 0.233, and I don't know how he did it, but it was centimeters cubed. So it's 0.233 centimeters cubed or 0.233 milliliters. It's the same thing. Okay, and it says, is this ring made out of platinum? So, and another thing is you can search the density of platinum up. So he looked it up. Density of platinum, PT, is 21.4 grams per centimeters cubed. Okay, so he's going to go ahead and get his density. So the density for his ring here is density equals to mass or volume, which mass and volume is right there. So 3.15 grams divided by 0.233 centimeters cubed. And he ended up getting 13.5 grams per centimeters cubed. And he's like, well, that's definitely not platinum. We don't know what the material is, so I guess he'll have to find material that has this mass here that looks like his ring. That would be the identity of his ring. Okay, so let's go to another question here about density. So I have two things. I have A and B. Density of A is 8.34 grams per milliliter. And then I have B, density of B is 2.46 grams per centimeters cubed. And it says, what? So the question is a little long, so I'm going to write it out and we'll read through it together, okay? What is the volume of a sample A that has the same mass as 23.64 milliliters sample of B. Okay, so basically you have sample B, you know what the volume is. You can take B and then you calculate how much mass this is of B. And then we'll find A to be the same mass as the mass of B. And then once you know the mass of A is the same mass of B, then you go ahead and take A and convert it back to volume. Okay, so when you have this, you have density. This is how we're going to use density as conversion. Every time you say grams per mil, that means A has a density of 8.34 grams. And that 8.34 grams is matched with 1 milliliter, exactly 1 milliliter. Okay, so I can actually write down for A, I know the information is 8.34 grams of A can be found in 1 milliliter of A based on my density information. That's one connecting piece right here. Now another connecting piece they gave us is the density of B. So I know that every time I see the density here, that means I have 2.46 grams of B can be found in exactly 1 centimeter cube of B, which, that's the same thing as 1 milliliter of B. Okay? So now I have milliliters of B. I want to go ahead and convert milliliters of B to grams of B. And then the grams of B is the same grams of an A. Then I'll take that grams of A and convert it to milliliters. So let's go ahead and start. I will take 23.64 milliliters of B. I want to turn it into grams of B. And then I know this grams of B is whatever this grams of B is the same as my grams of A. And I'll take the grams of A, turn it into milliliters of A, which is what the question was asking for. Okay? So we start here, 23.64 mils of B, always. So now I'm gonna go ahead and write it like this. Instead of writing multiply 1 over, all these lines here will just be, everything on the top is multiply, everything on the bottom is divide, okay? So 23.64 mils B, I wanna turn it into grams of B here. So I know mils of B and grams of B is the same, right? The connection is right there. So what you want to do is when you want to convert it to grams of B, you put the grams of B unit on the top. And then what you want to cancel off, when you want to convert away, you put on the bottom. So in this case here is 1 mil of B to 2.46 grams of B. So 2.46 goes up here. Then I have my answer. So my answer in this case, let's get the grams of B here, is 58.1544 grams of B. Okay? And then we want to take this number and then we want to go to the next step. While we're at it, since you probably already know about sig figs, we'll talk a little bit about here. So we'll actually be keeping 3 sig figs here because this one's 4, this one's 3. Well, I'll just underline the third number. I don't round it until the end, okay? So we write down, okay, now I know that's the grams of B. That means I have this many grams of A. So 58.1544 grams of A. And then I want to go ahead and convert it. I want to turn it into mils of A now. So I have to take grams of A on the bottom and cancel it out. So grams of A is 8.34 on the bottom and 1 mil on the top right there. And I will be able to get my answer now. This 1 here and that 1 here, these are exactly 1. Okay, when it's exactly 1, because it's is it 1.0, 1.00, it's actually 1.00000 forever 0. Those are what we call exact numbers. When you have exact numbers, they have unlimited sig figs. We don't consider them in the calculation. We just look at the smallest on the other numbers. So in this case here, this one had 3, this one has 3. My answer is going to have 3 sig figs here. So when you put this in your calculator, you take the top number, multiply with 1, divided by 8.34, you will get 6.97. as your answer. And that's my answer for this question right here. Okay? All right. So let's keep going here. So we were talking a little bit about sig figs here. Let's talk about why sig fig is important, okay? So when you're in lab, we use different instruments. Like, you know, certain instruments are more sophisticated. They give you more numbers, like more decimal places in your readings. Then you get more values, more significant numbers there. But then sometimes you have instruments that aren't that good and they give you a very little number. So how in the world are you going to be able to tell? So we have to basically, the more numbers you get from an instrument, the more numbers you have in your calculations for your data. But if you're limited in your equipment and you don't have that many numbers, you have to remember to keep the smallest number of significant figures, okay? So if your machine can only give you 1 decimal place reading, and then the other one gives you 10, it didn't really matter because you're limited by the one that's giving you 1 because you can't create extra numbers. You're limited by the, basically by the equipment that's the least sophisticated, okay? So in this case here, when we want to read things, we always read it to the point of where you can, and then we want to guesstimate the last number, okay? So for example, if you're reading a graduated cylinder, you're filling it up and we want to read the lower meniscus right here. And we know the lower meniscus is somewhere right there between these two lines here, okay? So it's 4, this is 3.5, 4, that's 4.5, that's 5. So it's higher than 4.5, right? But then that number here, well, we have to kind of guesstimate that number because it's between 4.5 and 4.6, right? So between 4.5 and 4.6, it's closer to 4.6, so I'm going to guesstimate as 7. So I say 4.57. So whenever you read an instrument in lab, read it until that number that you can see, and then the last one you want to go ahead and estimate, give your best estimate. So that last number can vary between students, okay, between individuals. And then if you have over here, it's marking every 1 gram, you will estimate that 1 decimal place after that. If you have markings every 0.1 grams, you will have the estimate on the second decimal place, okay? So based on these estimations here, we are sure that 5 is good, but we're not really sure about the 7. I mean, we kind of know it's close to 4.6. It's between 4.5 and 4.6, and it's closer to 4.6 than it is to 4.5. That's why the 7 is there. So the significance of it, we are basically limited by these 3 numbers. We can't say, well, it's 4.579989. You know, you can't create numbers after that because this is what you were limited to. You can only come up to 3 numbers. With this machine here, you can only come up to 3 numbers. With this machine here, you can only come up to 2 numbers. That's why these numbers have different significant figures, okay? Now, how do we count significant figures? A lot of times people forget to count you don't really know which 0 to count. Let me give you a quick hint here. If you write the 0 in your scientific notation, then it's significant. If you don't write it in the scientific notation, then it's not significant, okay? So in this case here, all non-zeros are significant. So 1.5 is 2 sig figs. Interior zeros are also significant. 1.05, that's 3 sig figs. Leading zeros are not significant. The ones in the front here. Why? Because when you write scientific notation, you don't write the 000 in the front. You just start from 1.050. You write the back ones, but you don't write the front. So in this case, you have 4 significant figures. Okay, so that's a really good way to determine which zeros are significant or not. If you write it in a scientific notation, it is significant. If you don't write it, then it's probably not significant. Now, trailing zeros may or may not be significant. After a decimal point is significant. If you put another 0 behind here, it will be 5 sig figs. Okay, now, if you have 150.0, so the trailing 0 before is significant if a decimal point is written. So if you have 150.0, that's 4 sig figs, right? That 150.00, that's 5 sig figs. Or if you have 1500.0, then you know all those zeros are significant right there. Now, if you write 150 like that, it's ambiguous. It's not a good way to write it. But if it's 150 just like that without decimal place, if it had a decimal place, we'll count 150 as significant. Because it doesn't have a decimal place there, we'll only count 1 and 5 as significant, so we'll call it 2 sig figs. When it's ambiguous like that, we'll always veer on the side of the smaller number, okay? So 1.5 10 to the power 2 will be obviously 2 sig figs. If you put 1.50 10 to the power 2, then it's going to be 3 sig figs, okay? So we definitely want to avoid being ambiguous. Now, these are just how to count them. And then when you have formulas, okay, or exact numbers. Remember we say, when I say 1 mil on the bottom for the density is exactly 1 mil. When it's something that's an exact number, it has unlimited sig figs, okay? So when you have 1 coin, 2 coin, 3 coins, exactly 1 coin, exactly 2 coins, then those are exact numbers, have unlimited sig figs. If you have a formula, 1 centimeters is exactly 0.01 meter, that's a formula that have unlimited sig figs. So we basically don't consider them during our calculations. Okay, now if you have equations, radius is half of diameter. So this 2 here divided by 2 is exactly 2. This also is unlimited sig figs because it's exactly 2, so it's 2.000000 forever 0. Okay, so when something has unlimited sig figs, we don't have to worry to count them in during our calculations because they're unlimited. We look at the other numbers that are smaller. Okay, so let's take a look at some examples here. All right. A better way to cover it. Look at the answers. Okay. So over here, how many sig figs do we have? 0.04450. Okay. Which zeros do we count? So in this case here, we will count 1, 2, 3, 4 as significant, but the zeros in the front don't count. Because when you write it in scientific notation, you write 4.450 and then times 10 to the minus 2. Okay, but you don't have to write in scientific notation. Just remember, you count these guys, but not the ones in the front because you don't write these guys as your scientific notation. What about this one? How many sig figs is this? 1, 2, 3, 4, 5. 5 sig figs, okay? This one's a formula. How many sig figs do you have? Formula have unlimited sig figs, okay? And then this one here, 1 point is in scientific notation, so all these zeros here count. So 1, 2, 3, 4. This one has 4 sig figs. Times 10 to the 5, this is just extra. You are actually going to be looking at this number here for the sig fig count, okay? Now, 0.00002. All the zeros in the front are not significant. You do not write them in the scientific notation. Therefore, this only has 1 sig fig. What about this one? This one's ambiguous, right? It doesn't really tell you. So you always veer on the side of caution and say this is probably just a 1 sig fig right there. Okay? So these are answers here. Make sure you practice. You can see these in your slides as well. Now, we want to talk about significant figures in calculations. So we always keep the smallest sig figs, okay? When you multiply or divide, we keep the smallest sig figs because we're limited by our least sophisticated equipment. So we always keep the smallest amount, okay? If you keep the biggest amount, it doesn't make sense because where are you getting those extra numbers from? Like one of them has 5, the other one has 2. Well, you should only go up to 2, then you shouldn't write all 5 down because the answer for 5 is not really accurate anymore because you're making extra numbers because this has been rounded so much. So keep the smallest sig fix. Remember, smallest one when you multiply or divide. So if you have 3, 5, and 2, you keep 2 sig fix in your answer. You never round them until the end for your answer. So I like to write down all the numbers here. If you had to mark down which was significant, then you would just underline the 5 right there, which is the second number to tell you, okay, this one has 2 sig fix. Okay, now and then you have this one here, 5.892. So let's zoom in a little bit. And then this is 3 sig fix, 6.10. Then you put in your answer has a lot of numbers in there in the calculator, but how many do we actually keep? We will keep 3 because we're limited by this guy, okay? So remember, multiply, divide, keep the smallest sig fix. No, but if you're adding or subtracting, you do not look at sig fix. You look at decimal places, okay? People always confuse that. So when you're looking for a plus and minus, you look at the smallest decimal place. So you see how this one has 2? Well, your answer better keep 2. This one has only 1 decimal place, your answer better keep just 1. Even though you have more numbers that they can calculate, what's significant is only limited by your smallest amount of decimal place right there. Okay? And then of course, you know, when you want to do calculations, you want to do the parentheses first and all that stuff. So let's do a few examples here. Okay? We'll do it together. We'll write it out together. You guys can practice along with me. So we'll have a few examples. Let me zoom out a little bit. A, the first one. 1.10 times 0.5120 times 4.0015 divided by 3.4555. Okay, so we want to do this one. Now I'm going to give you a few more and then you'll see sometimes the question on the test, they're a little tricky. They're like, based on this here, how many sig figs should your answer have? They don't ask you for the answer, they just ask you how many sig figs should you have. Now, if you were just looking, you might think, you know, yeah, I'm going to look and say this would be 3 because this one's the smallest, and I hope it's 3. But sometimes, I'll show you in later questions, it actually doesn't match up to what you think it should be. So you have to be really careful and punch in those numbers in your calculators and go ahead and work it out anyway, just to make sure. You'll see what I mean in a little bit. Okay, so let's go ahead and work this one out. So this is all multiply and divide. So we will keep our smallest number of sig fig. This one is 3, 4, 5, and 5 sig figs. So my answer should just be 3. All you do is you put in your calculator, okay? Put in all these numbers in your calculator, and you will end up getting a long number. So you get 0.652190. And you're like, well, that's a lot of numbers, but how many is actually significant? Only up to the third number. So then we can say, because of this, my answer that I want to pick is probably 0.652. Okay, so this one does have 3 sig figs as expected. That's cool. Okay, now, what about the next one? 0.355 plus 105.1 minus 100.5820. Now, if I asked you this question, well, how many sig figs do you think this answer should have? Well, first of all, you know, we're doing plus and minus, so we have to really be careful. Sig figs and decimal places are different. When you do plus and minus, you keep the smallest decimal place, and then they ask you how many sig figs you keep. Well, you want to look at the answer and then make sure the answer has 1 decimal place because you're limited by this guy, 1 decimal place. Okay, and then from that, you can decide how many sig figs the answer has. So in this case here, plus and minus, we just put it in our calculator and then we keep just 1 decimal place. In your calculator, you'll see a long number, 4.8730. Well, if it's just 1 decimal place, we end up right there. So you want to round. So anything that's 5 and higher, you round up. 4 and below, you round down. Okay? So because it's 7, we round up, so we go 4.9. So that would be 2 sig figs and 1 decimal place as your answer. Now, let's go and do another example here. So they say, what about this one here? Okay, here's my question. 4.562 times 3.99870 divided by, in parentheses, 452.6755 minus 452.33. And they're like, oh, well, how many sig figs does this answer have? Well, you should probably work this one out first, okay? And they'll give you choices maybe like 3, 4, 5, 6, 7, I don't know, all kinds of big numbers. It would seem like it would have a lot of numbers in there, but you'll be surprised at how many sig figs are actually kept in the end. So when you see this problem here, you want to do this in here first. Now, the one in the parentheses here is a subtraction, it's minus, so you want to keep the smallest decimal place. This one has 4 decimal place, this one has 2 decimal place. Okay, so my answer in this case here, I better keep 2 decimal place here, but I'm going to go ahead and write down all the numbers, but just underline which one I remember I have to keep. So it's 0.3455 as my answer, but I know I have to stop at the second number. Okay, then let's continue with the other parts. I'll write down 4.562 times 3.99870. So this one has 2 decimal place, 2 sig figs, lots of sig figs, lots of sig figs. So my answer should have only 2 sig figs, okay? Which would then be 53 here once you put it in your calculator. It's a little unexpected to get just 2 numbers based on all these numbers of bits because it's limited by this operation right here. Okay, so let's go to the next question. It says 14.84 times 0.55 minus 8.02. Okay, they'll ask you, how many sig figs does this one have in the answer? And you will never guess it. Well, I guess you could if you worked it out. But the answer for this one here is only 1 sig fig. You're like, what? How come? So let's take a look, okay? You do this inside here first. This is 4 sig figs. This is 2 sig figs. So you will be keeping 2 sig figs in your answer. So when you put this in your calculator, you get 8.162 as my answer. And then I remember I need 2 sig figs, so I'm going to go ahead and underline that right there. Okay, the second number because it's 2 sig figs. And then you go, okay, let's continue, minus 8.02, 1 decimal place, 2 decimal place. How many do I keep in my answer? Only 1 decimal place, so it's 0.1. That's why we only have 1 sig fig in our answer, because it ends up being 1 decimal place. Okay? All right, let's try another example. 9.992 times 3.200 plus 0.610. Okay? How many sig figs do you think we should keep in our answer? 3, 4, 2, 5? We don't know. Okay, so let's take a look. We do the ones on the inside. This is 4 sig figs. That's 4 sig figs. We will be keeping 4 sig figs in the answer right there. So on your calculator, you get 31.9744. But then we know we're limited with 4 numbers, so I underlined the 4th number right there. Okay, and then we want to continue with plus 0.610. Now when you're adding, you're looking at decimal place. So this is 2 decimal place, this is 3 decimal place. How many do I keep in my answer? Only 2. You're limited by your smallest. So when you get your answer is 32.58 because I'm limited by my second decimal place right there. And this would give you 4 sig figs. Okay? Now let's do another example. 1.302 plus 953.2. And then you want to divide by 2.0. So we're going to do this addition in here. Now this addition here, because we're adding, we're looking at decimal place. Keep the smallest, 1 decimal place, 3 decimal place. We will keep 1 decimal place in your answer. So you write down the answer. It's 954.502. Keep all the numbers for now. Underline which one it stops at, the first decimal place. And then we say take this and divide by 2.0. So this is 4, 1 decimal place, 4 sig figs, 2 sig figs. My answer should only have 2 sig figs. So 2 sig figs, my answer would be 4.8 times 10 to the power 2. If you just wrote 480, it would be kind of ambiguous. So you write 4.8 10 to the power 2. Okay? Now, G, we want to do the last one here. 143.7 minus 121 times 2.06 and then divided by 0.600. Okay? So for this one here, we'll do the one inside the parentheses, 1 decimal place, 0 decimal place. So how many you keep? 0 decimal place. Okay? So I'll do this one in here. You get 22.7 when you subtract it. But remember, we keep no decimal place. I underline my 2 there. And then I do times 2.06 divided by 0.600. So that's 3 sig figs, 3 sig figs, 2 sig figs. So my answer will only have 2 sig figs. Okay? So that's what we have for our significant figures. Make sure you guys practice. It's very important to practice this until you get familiar. It's really, really crucial to know this in lab as well. Okay? Now, let's keep going. We're almost at the end of the chapter. So over here, let's go ahead and talk about precision and accuracy. So in lab, we want to have data or results that are accurate and precise. That's your goal, okay? You won't always get it, but we always try to get it. So let's talk about precision and accuracy. Accuracy is how close you are to the correct answer, okay? How accurate are you? How close are you to the correct answer? Precision means how close your answers are to each other. So the reason why we want to go ahead and do multiple trials in your experiments is because sometimes maybe one of the trials you made a mistake you didn't know. If you did just one, you would have been wrong. But if you did 3, maybe you found out the first one was wrong. Maybe the second and third one is correct. So you can kind of see, you know, how precise it will be. Ideally, your answer should be precise, close to each other, and accurate, close to the correct answer. Okay? So here's an example here. Look at this one here. It's inaccurate and imprecise. It's not accurate and not precise because look, it's all over the place. If I told you to measure basically a piece of a weight or something, and you put it on the balance, and every time you put it on balance, a different number came out. You're like, oh, what's going on here? This is weird. So that would be not precise. Okay? How in the world can you tell your accuracy? Well, you take your average of all your trials and you get an average number. And you can see if your number ends up being close to the actual answer, then you're accurate. If not, then you're not accurate. In this case here, the student is not accurate and not precise. Now, if you're precise, all close together, but then it's off the correct answer. Like you're always getting something that's kind of slow, small, right? You're always a little under. So this one here would be precise but not accurate. A lot of times this kind of problem could be an instrument problem. Or maybe you're just doing the experiment wrong the whole way, okay? But sometimes if your balance is not not functioning correctly, you didn't calibrate it correctly, then it's going to always give you reading that's a little bit off. But it's going to be off in one direction. Okay, so that's something we call a systematic error. Like something that's always off in just one, too high or too low in one direction. It's probably because there's a systematic error, like you're either doing it wrong a certain way, like you're forgetting to put something in your flask, or maybe you're weighing it and your balance is off. That's how you get a systematic error. Random error is like this, up, down, everywhere, all in all directions. Okay? And then to minimize random error, we do more trials. The more trials you do, the better you get at it, the closer the value will start to come together. Okay? Ideally, in our lab, we want something that's accurate and precise. If you want to get 10 and you weigh it, it's almost 10 every time, then that's great. Okay? So you will have to be able to tell based on some data which one's accurate, which one's precise, which one's not accurate or not precise. Now, we will be using a lot of dimensional analysis to solve for our problems here. So just keep, we want to just go ahead and remind you, the unit that you want goes on the top, the unit that you want to cancel out goes on the bottom. And you cancel out, and we always go step by step, cancel top and bottom until we get our answer that we want. Okay, that's dimensional analysis. So let's do one last problem before we end our chapter 1. So in this case here, we were already doing a density as conversion factor earlier. So here's an example, but we did a way better example a little bit ago in our question right here, where we cancel off the unit that we didn't want and all that. That's what we're going to be working on. So one more question, okay? Before we end chapter 1 here. So write it out together. Zoom out a little bit. So we want to talk about fuel in a jet, okay? The mass of fuel in a jet must be calculated before each flight. To ensure that it's not too heavy to fly, okay? And then it says a 747 is fueled with 173,231 liters of jet fuel. If the density of jet fuel is 0.768 grams per centimeters cubed, what is the mass of fuel in kilograms? Okay, so they want you to convert a few units. They gave you the density, right? So they gave you 173,231 liters of fuel. They told you the density was 0.768 grams per centimeters cubed. That means 0.768 grams of fuel is found in 1 centimeters cubed of fuel, which is 1 milliliter fuel. Okay, now remember, what's the conversion between milliliter and liter? 1 liter is 1,000 milliliter, which is 1,000 centimeters cubed. That one I want you to go ahead and memorize like this and this. That saves you a lot of time, okay? So, and then we also have to remember, what in the world is the conversion to kilogram? Well, kilo means 1,000. So 1 kg, 1 kilogram is 1,000 grams. Okay, so these are all my conversion units I believe that we needed. Okay, let's go ahead and start. We want to go ahead and start from liters of fuel. So I want to go from liters of fuel right here that we're given, and then I can probably use the density to get it to grams, but then I can't get straight to grams because I have to go from liters to milliliters. So I'm going to go from milliliters to milliliters of fuel, and then I can say, well, I know that in centimeters cubed fuel, and then from centimeters cubed, I can use the density to turn it to grams of fuel. And then I can use the grams to kilograms relationship to get it to kilograms of fuel. Okay, so that's my plan right there. Let's go ahead and start. 173,231 liters of fuel. And then I'm just going to do a big straight line so I don't have to write multiply, divide every time. Fuel liter, I'm going to turn it to milliliters, and fuels, centimeters. So I can actually go from here to here with that's one, but we'll just step by step. Okay, 1 liter of fuel is 1,000. So 1 liter of fuel, it's on the bottom to cancel off, is 1,000 centimeters cubed. Milliliters. Oops, I got too excited there. Well, technically we could go there straight, but we'll do it step by step. Okay, and then let's do one more step. 1,000 milliliter is 1,000, so I can do that. Or 1 is 1, doesn't matter, you can use either one. We can do 1,000 or 1, doesn't matter. We'll do 1 milliliter, fuel is 1 centimeters, fuel, 1 centimeters cubed. And then centimeters to grams using the density right there. So centimeters is going to be canceled on the bottom. So 1 goes on the bottom right here. And then I'll go 0.768 grams of fuel on the top. And then once I get that, I'm going to do grams on the bottom, cancel it off. See grams and grams on the bottom? And then I want to convert to kilograms of fuel on the top, which is 1 kilogram for 1,000 grams. Okay, so you get liters, cross off, milliliters, cross off, centimeters, cross off, centimeters cubed, cross off, grams, and then cross off. Then you have kilograms as your answer. Okay, so what you have here in the end, when you put everything, and you want to keep in mind how many sig figs you can keep. Well, you have 3 sig figs in your density and 6 in your original number. So you end up keeping with 3 numbers right there. So I go at 1.33 times 10 to the power of 5 kilograms. So the way you do this in your calculator is take this times this times this times this times this, divide by this, 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 this. So you just hit divide every time, okay? And then you should be able to get this answer. Now that is the end for chapter 1. We will continue on to chapter 2 in the next recording.